here we go. Okay, so today's lesson is a bit of a review. So right away when you look at that first question, solve for x, we should notice a few things. We should notice we have a cos x and we have a tan x. So they're not written the same trig ratio, but we should be able to turn that tan x into a sine x over cos. Using our knowledge about what tan x equals, you'll recall that identity from last year. So a few things that I'm going to do here. I'm going to make myself a note that I know that cos x cannot equal 0. That if any of my answers occur that cos x is equal to 0, that means it's going to be undefined for this equation. The next thing I'm going to do is I'm going to multiply each term by my cos x. So again, you'll recall the difference. I cannot divide out a possible solution, but I can multiply each of those terms by my denominator. Okay, so now I'm hoping we'll still notice we have this two different trig ratios. I have a cos squared x and I have a sine x, but you'll recall from last week that we can then change that cos squared x into a 1 minus sine squared x using our Pythagorean identity. We can expand. And I'm just going to divide out my leading coefficient of a negative, just because I prefer to have my leading coefficient be positive when I go to factor. But again, just personal preference, it doesn't have to be that way. And then I look to factor. So I'm left with a 2 sine x plus 1 and a sine x minus 2. So I have sine x equals negative 1/2, or a sine x equals 2. So at this point, we should be looking at this and going, okay, sine x equals 2. That provides me with no solution. There is no angle where my y value on sine is 2. And then sine x equaling a negative 1/2. Sine is negative where the opposite sides are negative. So I know I'm in quadrants 3 and quadrants 4. Use my special triangle. And so therefore I know, I'm just going to write it up here so I have more room. Therefore x is going to equal 7 pi by 6, or x is going to equal 11 pi by 6. And if that was the answer that you were looking at to calculate, we are so close to fully answering this question. I'm hoping you'll notice that my original instructions up here just say solve for x. There are no restrictions on our domain. So at that point, I would have to write my general statement, so plus 2 pi k. And that's just our quick review on those solving equations that we did last week. So again, the point of today's lesson is to kind of remind us of key properties of our equations and of our graphs so that we're really prepared for when we go into tomorrow's lesson on working with our trig application questions. The next piece that I want to review with you is just identifying key information from our equations. So one, we just dealt with solving equations. Now we're looking at identifying key pieces of information from our function. And then in our next examples, we are going to look at our graphs and create the equation. So we're kind of working in all directions here today. So I want you to take a minute to fill in those key properties for each of those functions that you see there. Okay, let's see how you did. So to start with our first function, we have our amplitude, right, which is half the height, should be 5. So it should not include the negative. Okay, it should be that positive 5. You'll recall our amplitude was the absolute value, meaning that it was a positive value. Our period, so we know we have a horizontal stretch by a factor of 1/2, so we've cut that in half. So it used to take 2 pi on our sine curve was cut in half, so it only takes pi units. Now, Again, you have your trusty little friend of period equals 2 pi divided by k. Should you want to sub that in to calculate that way. And now our phase shift, we have not shifted left or right. So we have a phase shift of 0. And our vertical shift, we have shifted 3 units up. So just writing a +3 doesn't actually describe to me what has happened here. Okay. So that's all of our key information there in A. Now in B, I'm going to argue probably the thing that would be what some of us might forget is just to make sure we common factor out that 4 so that the coefficient of x is 1. So in order to shift left or right, we need that to be for the value of 1x. Awesome. So at this point, we can tell from the beginning of our graph that our amplitude is 3. Our period, so again, we've been horizontally stretched by a factor of 1/4. So we have 1/4 of what our graph was. So what was at 2 pi, we've cut that by 1/4. So our period should be pi by 2. And again, I was just using that 2 pi divided by k. I was just thinking about it in terms of what's happening to my graph, but I guess I could have subbed that into the equation as well. Phase shift, we notice horizontal is opposite of how we read it in our equation, so we have a shift of pi by 4 units right. And we have our vertical shift, we are shifting down 1 unit. So again, the point of that example was to get us thinking about where are the key pieces of information coming from in our equation. So this is really where we're starting to get to in today's lesson, right? So now you have been given the graph, and I'm asking you to write both a sine and a cosine function whose graph resembles this graph and then the next few graphs that we're going to do. So a few things here. You'll notice we looked at the equation to identify some of those key properties. So now let's look at the graph and again identify some of those key properties. So I'm just going to, I think it's a bit difficult to read what these values are. This is a pi by 8. This was a pi by 4, a 3 pi by 8, and what would be a 4 pi by 8, which is just a pi by 2. Okay, so just our key. The grid there, I'm not sure if yours comes out as fuzzy as mine does, but just in case. Okay. So if we think about that base sine or cos function, so let's start with thinking about, we have our a value, so we need our amplitude. We're either having a sine or a cos function. We have our k value potentially, that horizontal stretch. We might have a phase shift. And then we have that shift up or down, which we also can think about as our sinusoidal axes. Right, so let's start with a few things. What do we know? So let's start to think about these pieces. So our amplitude, we know we span from a height of 2 to -2. So that total distance is 4. If I were to cut that in half, because my amplitude is half my height, I know that I have an a value of 2. If I then start from my max or my minimum, I know that this has a y value of 2. If I subtract 2 from it, I get to my equation of my axes. And the reason why I subtract 2, because that was my amplitude. Or I could work from my minimum, which has a y value of -2, and I add my amplitude, and again, that gets me up to my equation of my axes. So again, very basic on this graph, but a property I'm hoping that we can think about in our upcoming examples as well as on our word problems tomorrow. So we know we have a c value of 0. So really that equation of our axes here is at y equals 0. And so the next piece that we want to think about is what's happening with that k value. So if I go through one full rotation of my curve, I know that the period of this is pi by 2. So we can think about this in a few different ways. You can go, okay, originally the period of this would have been 2 pi. So to get to a pi by 2, I would have had to horizontally stretch it by a factor of a quarter, which means my k value would have in fact then be written as a 4. If you're going, okay, I'm not quite sure how we got that. Again, we have our trusty little period equals 2 pi over k. In this case, we know our period is pi by 2. It takes pi by 2 units to get a full rotation. Rearrange. My pi's will divide out. I'm going to multiply by the 2, and I get that k equals 4. So again, you can think about it in more than one way. I would not need to see what I have written there in green, okay? But that's kind of the math behind it. So at this point, we know we have our amplitude, we have our stretch, and we have our shift up or down. So we can start to build these equations. Okay, so let's think about, those are going to stay the same regardless of if it's a sine or a cos curve. So let's think about that for a moment. I have y equals 2 sine, and then I have 4, and I might have a shift, and I'm not shifting up or down, and then I have my cos curve, and I don't know yet if it's being shifted to the left or to the right. So what I'm hoping you'll notice from that is our stretch, our vertical stretch, our horizontal stretch, and our shift up and down are the exact same regardless of if this is a sine function or a cosine function. So I'm going to just clean this up a bit just so we can see what's happening here. Okay. So I'm hoping we can both notice that the easiest way to describe this function is to recognize what's happening here. So we start at 0, 0, and our curve is rising. And I'm hoping we all recall that our sine curve starts at the axes, at the equation of the axes and the y-intercept, and it rises. So what that means is our sine curve is not going to have a phase shift left or right. But in the question, we've been asked to write both a sine curve and a cos curve. So we know that our cos curve will in fact have a phase shift. And there's a number of different ways that we can write that cos curve. So let's first think about, where does our cos curve start initially? Our cos curve normally starts at the max and it falls. So in this case, our cos curve, after it's been vertically stretched, would still start at its max. Its max would be at 2, and then it falls. Well, what happens to that curve? Where do I see a maximum and falling? I see that pi by 8 units to the right. So what would have to happen to my original cos curve after I vertically stretched it, horizontally stretched it, in order for my original cos curve to lie on top of this new curve that we see? I would have to shift that pi by 8 units to the right. And again, because inside of our function is opposite of how we read it for our horizontal, that would be represented with an x minus pi by 8. I'm hoping there's a few other ways that we could have thought about this. We could have potentially reflected our cos curve and said, okay, well, if I reflect my cos curve, it's going to start at a minimum to my original cos curve. And then in order for it to represent the graph that we currently have, we would have to shift it to the right 3 pi by 8. So a different option for this equation of these curves could have been a -2 cos and shift it to the right 3 pi by 8. And again, its amplitude and its shift up or down would remain the exact same. So those are just some options of how we could have written this cos curve. So if you're asked for a sine or a cos curve, I obviously would suggest that in this case, this would be our most efficient way of writing our sine function. I would argue that for our cos function, this has fewer transformations to it. So that would be our next most efficient equation. However, if I asked you for both a sine and a cos function to represent this graph, you could give me either of those functions there. You would not have to list every single one. You'll notice for the purpose of today's lesson, I'm going to list more than what you would need to see just to make sure that you get a full understanding of these functions. Okay, so for this question here, let's start by thinking about those key properties that we have. So let's recognize some key features of our graph. So I noticed that my maximum has a y value of 5, my minimum has a y value of -1. So I note that the span of my y values goes from 5 all the way to -1. So we've gone 6 units from our max to our min, and which means if my amplitude is half of that, my amplitude would be 3. To help me find my equation of my axes, I know that I can take my minimum and I can add my amplitude. So if I go up 3 from -1, or I can go down 3 from a positive 5, so 5 minus 3. Either way I want to think about it, I know that the equation of my axes, that middle graph part of my graph vertically, is going to be at y equals 2. So my c value is 2, meaning my equation of my axes is in fact at 2. So I'm going to just clean that up for a second. So if we know our equation of our axes is at 2, I'm just going to show that these are some of my key values on my curve. The next piece I want to think about is it takes, for a full rotation to occur, it's taking 2 pi by 5 units. So if my graph is normally a 2 pi, and now it's being horizontally stretched by a factor of a fifth, that means my k value is going to be a 5. So again, if you want to think about what that looks like, one, I had 2 pi, and it's now a 2 pi by 5, which means really I horizontally stretched it by a factor of a fifth, and I know I write that into my equation as its reciprocal. So again, one way of thinking about that. Another way is to more so putting those blinders on, but we can go to that equation of period equals 2 pi by k, and I know my period is 2 pi by 5. And obviously, we can tell pretty quickly by looking at that k is equal to 5. Again, I do not need to see what's written there in green, just some extra information for us. So again, what we could recall from that last example is that our a value, our k value, and our c value, and really I don't care if you remember what those letters stand for, but we know our vertical stretch, our horizontal stretch, and our equation of our axes are going to be the same for both our sine and our cosine function, right? So we have 3 sine. I know I'm going to have a 5. I may or may not have a shift left or right, and then I have a shift up 2. Cos, same thing. So those are those key pieces of information that will fill in both spots of my graph. So now when I look at what I have, I know if I'm starting at where my equation of my axes and my y-axes meet, that since my graph is there, I know that that's going to represent my sine curve. My sine curve starts at the middle of my graph and it rises. So I notice that that's happening here with this function. So what that tells me is I do not have a phase shift for this function if I want to write it just as my sine curve. So let's clean that up. What that does mean, though, is I will have a phase shift for my cos curve. So again, I know cos would start at the maximum of my graph, and this has been vertically stretched and shifted up and horizontally stretched. So that would put my cos curve starting at my max. But on the curve I've been given, I know I would have to shift my cos curve to the right, pi by 10. And so that would allow me to write both a sine and a cosine function. But those are just some of many options that we have. So if I reflected my curve at 3 pi by 10, I have my minimum. So if I reflected one of my curves and started at my minimum, that would represent a reflected cos. So starting at my minimum and increasing. So if that's where I wanted, I could start at a reflected cos, but in order for that graph to actually represent the curve that we see, the function that is graphed here, I would have to move that to the right 3 pi by 10. So an alternate equation for cos could be a reflected cos, which means I start at my minimum. I'm still going to have the same horizontal stretch factor. But obviously this, what I have here in green, doesn't represent the function that we've been given. So I would have to move that function 3 pi by 10 to the right. Need an x in there. And that would be another way that I could represent a cos function. Okay, so that's one option for our cos function. An option for a sine function is instead of starting at the middle of our graph and rising, we could say, well, technically, what if we started at the middle of our graph and we fell? I could still represent sine in that case, but as you can tell, that's not going to represent the function we currently have. So if I wanted to start at sine and or start at the middle of my graph and fall, where that actually occurs on the graph we've been given is here. So in order to represent the function we've been given, I would have to take my reflected sine function and I would have to shift it to the right pi by 5. And then now that could be an equation that could represent the function that we've been given. Okay, so we're shifting. So we're taking our base sine function. I'm applying a reflection, a vertical stretch, a horizontal stretch, and a shift up. And this is where I get to. But I need that to actually represent the function drawn here in black. So in order to do that, I would have to also incorporate a phase shift, and that would involve me shifting it to the right pi by 5. So let's see how we did. So again, if I think about where my y values are, I have a minimum at -4, a maximum at 2. So the distance between from 2 all the way to -4 is 6 units. So if I cut that in half, I'm going to have my amplitude is equaling 3. So then from there, if I want to find the middle spot of my graph, if I work from -4 and I go up 3, I get to -1. Or I could start at 2 and I could go down 3. And again, I get to that -1. So I know that the equation of my axes here is at -1. So my C value is going to be at -1. The next piece of information, if I think about what's happening to my horizontal stretch, has it been horizontally stretched? Well, we can tell that a full rotation is going to take us to 4 pi. So we know our graph has been horizontally stretched by a factor of 2, which means when we go to write that k value, our k value will be 1/2. Because we know in our equation that's going to really be described as a horizontal stretch by a factor of 2. Again, if you're unsure, rearrange, and we get that k is equal to 1/2. All right, so again, I'm really hoping I'm hitting home that point that our amplitude, our horizontal stretch, and our shift up or down are the same regardless of if it's our sine or our cos function. All right, so now let's see what's happening with these graphs. We notice our curve starts at that equation of the axes and it falls. So that means it's representing for us a base sine curve, except the sine curve has been reflected. So my graph that I can write with the fewest number of transformations is a reflected sine curve, which would not require a phase shift. Which does mean, though, to write our cos function, it is going to reflect or require some type of phase shift. So again, I know my cos curve can start, so we can kind of choose here. I can start with let's start with cos. We'll start with cos being at its max. We know cos starts at its max and it falls. Didn't really draw that as a stretched cos curve. It falls, okay. We notice that where that actually happens on the function that we're working from is at 3 pi. So in order for our base cos curve to represent the function we've been given, we are going to have to shift it to the right 3 pi units. So we've given one sine and one cos curve, so technically we've answered the problem being given to us. But I'm going to encourage us to try to find an additional sine and an additional cos function. So exactly on one of our cos ones, we could start with the reflected cos, which means we start at our min and it's rising. So again, we've applied these transformations to our base function. The last transformation that we need to include to ensure that it represents the function we've been given is to now shift that to the right pi units. So again, we reflected our base cos curve. We vertically stretched it by a factor of 3. We horizontally stretched it by a factor of 2. And then we shifted it to the right pi units and shifted it down 1. And as a result, we've ended up with that graph that we've been provided. Okay. And so then my other question I asked was just, can you represent for me another sine curve? So we started with the fewest number of transformations with our sine curve, which involved just a reflection. So let's say you did not see that reflection. You went, okay, sine starts at the equation of the axes and my y-intercept, and it rises. So let's say we started there. Well, when does that actually occur on the graph we've been given? Well, it occurs at 2 pi. So if we chose not to reflect our sine curve, we then could have used a phase shift to shift it to the right 2 pi units. So again, you would not be required to give this many examples. However, I think it's just important for you to see the different options to kind of gain that full picture idea. So in this last example, I am asking that you write for me a cosecant and a secant function whose graph is represented with the one below. So I want to give you a minute or two to kind of think about the information that you have and how you can relate that to those equations. So take a minute to do that. Okay, so let's see how we're doing. I'm going to start by just labeling some key points here, just in case you can't read them as clearly on the graph. Okay, so I want you to think back to your base secant or cosecant curve. And I'm hoping you'll think about those key values. We had our local minimums and our local maximums were at 1 and -1. So that distance between our points on our base curve spanned from 1 to -1. So that distance between them was a 2, which we know if we divide that by 2, we get 1, and our amplitude, or that a value rather, because we know that by definition we don't have an amplitude of a cosecant or secant graph, but that a value was a 1. We can use that information of that distance between those local max and local mins to help us to find that a value. And what I'm noticing here is we span from a y value of 1 all the way to -3. So that's 4 units. So if we were to divide that in half, take half that distance, we are going to get the value of 2. So our a value here is a distance of 2. Right? So that if we look at the distance between those curves, it spans 4 units, and half of that will give us that a value. So we do notice we have a vertical stretch here. That means we have a vertical stretch by a factor of 2 for this function. Okay. We can still use that information to think about, has this function been shifted up or down? So I can use that information to go, okay, from -3, if I go up 2, that places me at a y value of -1. Or I could go from 1 and go down 2. So again, the middle of our graph is going to be at -1. So we have shifted down 1. So I'm using the same types of pieces of information as I did with my sine and my cos curve. The last piece that we want to think about is that horizontal stretch. Just by looking at my curve, I can see it spans from 0 to 2 pi. So there is no horizontal stretch. So my k value would just be a 1. And we notice that there has not been, from one of those base curves, I am starting on that axis at my key value, and so that there has been no phase shift because I am starting at my minimum. So the next piece to think about is, okay, which graph starts at my minimum, that local minimum, and rises? And so if you're going like, oh, I don't remember, we can think about what we have in terms of, so our reciprocal functions, right? So we can think about, well, what function would that be the reciprocal of? And that would be the reciprocal of our cos function. The one that starts at its max provides us with a local min with that reciprocal. So we know the reciprocal of cos is secant. So what we have here is our base secant function. So again, the reciprocal of cos is secant. So I have 2 secant x minus 1, because again, we did not have a horizontal stretch. So that's just a reminder there in case you're kind of forgetting those base curves. Okay. So that should tell us a few things. We know we have our cosecant function. We know that it's going to need a phase shift, but we also know it has similar key properties to our secant curve. And what I'm hoping we'll recall is our cosecant curve is the reciprocal of sine. And our secant curve, if it's a reciprocal of sine, means that it normally has asymptotes at 0, pi, and 2 pi. which we notice is not the case here. So what that means is we have shifted our graph. We need to shift those asymptotes of our base sine curve to the right pi by 2. And that should represent for us our secant and our cosecant functions of this curve. So we can use those asymptotes to help us with what's happening with our function here. And so now you're able to look at the graph and write for yourself a secant, a cosecant, as well as for the questions we did before, a sine and a cosine graph. So with this graph, you should have a problem with that last equation. Because with that last equation, all we did was we went, okay, well, I saw an asymptote. We're really used to just shifting things to the right from all of these other functions. But we should be shifting this to the left, okay? So please just don't put the blinders on of we're shifting to the right. This is what's happening. So I want you to think about. So I've drawn in red here. I'm hoping we can all see that red. Where our base cosecant graph has asymptotes. And I'm also hoping then we can picture those where this should be, let me just get my bearings here. What you see here in red should be what our base cosecant graph looks like. So I'm going to try to highlight it just so we can, I'm hoping this makes it easier, not harder. So that should be our base cosecant function. But what you'll notice, if that's my base cosecant function, it needs to line up with this portion of my curve and this asymptote. Which means in order for that to occur, this piece has to get shifted to the left pi by 2. This has to get shifted to the left. My asymptote here actually has to be shifted to the left pi by 2 in order for all of these values to actually lay on top of that black graph. Okay, so in fact, this should be a 2 cosecant x plus pi by 2. It should be shifted to the left pi by 2. Okay, so please just keep in mind what that full picture does look like. And by all means, if you need to draw on your base curve with some of those transformations to it in order to see that shift, absolutely. But please keep in mind we're taking our original function and we're transforming that original function so that it turns into the equation of the graph that we see in front of us.